Yeah. Okay, so our last speaker for tonight is David Williamson. He is a postdoc in the astrophysics group at the University of Southampton. He is going to tell us a little bit about supermassive black holes, so not just black holes, supermassive black holes, and actually have some. Oh, sorry, where is it? Oh, or was it?
Oh, sorry.
You used to play the trombone in a ska band for like a few.
Okay, so I was asked to share a fun fact to prove that I don't just do astronomy all the time. And the best I could think of was that I played trombone in a Christian ska band for about 3 months and never played any gigs. So, there you go.
Okay, let's thank Dave.
Okay, so yeah, I'm David Williamson. We work here at the University of Southampton. And I'm going to talk to you tonight about supermassive black hole space gas mystery. I just want to point out that the only reason I'm using PowerPoint and not Keynote is because PowerPoint has garish word art that you can use, and it's animated. Alright, so supermassive black hole space gas mystery is a title that tells you nothing. So what actually is this mystery, and what have we kind of done to try to solve it? So basically, the gas around black holes is in the wrong place. Okay, that's my sort of dramatic version. Here's the version that actually tells you something, which is a lot boringer. This is why the papers that I write end up far too long and with too few citations, is because I try to be precise. The gas around supermassive black holes is not where we'd first expect it to be, but we can explain it, probably. It's not quite so punchy, but that's kind of more where we're going. Okay, so what are we talking about there? All right. Well, this is obligatory. Yeah. So this is a real photo of a supermassive black hole. Nothing I say is going to be as cool as this, so you can go. So this is done by the Event Horizon telescope, which is a collaboration of a bunch of radio telescopes from around the world. They collected the data. It actually took them ages. Like, one of the things that was slow about this project, why it took them so long to take this photo, is because they had to literally ship hard drives from Antarctica in order to put everything together. And this is a picture of a black hole. The bright stuff is where the black hole isn't, and the dark bit in the middle is where the black hole is. But there's maybe something a little bit puzzling about this. Okay, so this bright stuff is hot gas that's right next to the black hole, and it's getting like gravitationally lensed and all sorts of stuff, and I could talk for a half hour about gravitational lensing if I knew anything about it. But isn't that a little bit odd, right? Like, because the first thing you learn about black holes is that they're huge and they're massive and they suck stuff up. So why is there all this hot gas around it to give it this sort of background for you to see this black hole shadow against? So that's the first question, is if the gas around black holes is in the wrong place, okay, but why is there gas around black holes at all? Shouldn't the black holes just suck it all up? Alright, so surprising fact number one, it's actually really hard to hit a black hole. So let's say, let's ignore supermassive black holes for a second. Let's look at like star-sized black holes. Let's suppose that we take the sun and we allowed the sun to collapse all the way down into a black hole. Now the sun's not going to become a black hole, I'm playing pretend. We can do that, I'm a theorist. So if we turn the sun into a black hole with the same mass, we didn't lose any mass and eject or whatever, how big would that be? How small a target would that be to hit with a star or a spaceship or whatever? Okay, so this is the sun, this is the Earth to scale. I mean, the distance is not to scale, but that's the size of it. Alright, so let's see. Can you see the black hole here? No, it's not there. It's too small. Alright, let's zoom in. This is Earth. It's still too small to see on this. How small do you reckon we have to go? Alright. This is a planet, you know it. It's Earth. Still too small to see. If the sun turned into a black hole, it would be much, much smaller than the Earth. Let's continue to zoom in. This is Europe, which we are currently part of. It's still much, much smaller than a continent. Alright. This is a smaller part of the universe known as the British Isles. I have now, not sure if you can see it because it's fairly low down on there, but I have actually drawn to scale the the black hole. Can you see where it is?
Just about the other one.
Let's zoom in a little bit more. Or if you prefer, if you're a Saints fan, you can. So, if the sun was shrunk down to a black hole, it would be about 6 kilometers across, which is incredibly tiny. So it's actually quite a hard thing to hit. Like if you think about that stars are light years apart from each other, that even the distance between the Earth and the sun is really big. Hitting an object that small is pretty hard. You'd have to be targeted straight at it in order to hit it. So it's hard to hit a black hole, partially because they are very small in size, not in mass. But that's a sun mass black hole. What if we look at a supermassive black hole? So the supermassive black hole that the Event Horizon Telescope saw is a particularly big supermassive black hole. I think it's about 6 billion times the mass of our sun. So it's going to be, it turns out, the math actually turns out really nicely, that the size of a black hole, its diameter, is proportional to its mass. So if it's 6 billion times more massive than the sun, it's 6 billion times bigger in terms of radius as well. So how big is that? It's reasonably big, but not as big as you might expect. So the sun I have expanded so you can actually see it. This is Pluto's orbit, which is irregular because Pluto's orbit is weird. And this supermassive black hole is, maybe 6 times the size of Pluto's orbit, something like that. So it's much bigger than the solar system. Okay, so that seems reasonably big. But still, on an astronomical scale, it's not actually that large. So, we are here. This is Alpha Centauri, which is a double star system, which is nicely visible from New Zealand in the southern hemisphere, but not from England, just saying. And the distance from our sun to Alpha Centauri is 400 light years. How big on this scale do you reckon this supermassive black hole is? That big or that big? Turns out it's that big. And I measured the pixels, got it right. So that's about how big it is. It's actually, I think on this projector, it's not even showing it as a circle, it's just a dot. So if you can imagine that you've got a bunch of stars floating around the Milky Way, the odds of one actually hitting a supermassive black hole and getting all sucked up into it are actually pretty low. They're really, really tiny. However, of course, we know that gravity is important. That's kind of the point of black holes, is they have really, really, really strong gravity. So, okay, maybe they're really small, but maybe their gravity is strong enough to suck everything up, something like that. But again, that does less than you might expect. So let's go back to this idea of the sun turning into a black hole. Again, the sizes are not to scale here. If we converted the sun into a black hole the same mass, what would happen to Earth's orbit? And I've got a few different options here. You could say A, okay, black holes have a lot of gravity, it's just going to suck it straight up. B, okay, it's got a lot of gravity, but the Earth's got some momentum to it, so it's going to sort of spin around and spiral inwards, get sucked in. C, it's going to just keep going, nice circular orbit like it was before. Or D, well, we've shrunk it, so it's just going to fly away. Something like that. Okay, what do you reckon? Shout it out.
B.
Yeah. So, this is Newton's gravitational law. I'm not sure what it's called, but we know the gist, we know the maths, we know the calculus, I don't know the names. The thing is, like, gravity is caused, unless you're like right on top of a supermassive black hole, any black hole, unless you're right on top of a black hole, its gravity is just really the same as any other object with that type of mass. So you can go in nice circular orbits around black holes. This means that you're not going to just suck stuff up. You can have things in nice orbits and be stable for quite a long amount of time. So, how does a black hole suck up anything? How do they grow? The short answer is slowly. So the basic picture is you have random crap flying in from everywhere around a black hole, and this gets accelerated and slingshotted around by the gravity of the black hole. Even though, as we know, it's quite hard to hit the black hole itself, its gravity can still accelerate things, give it some speed. And if you've got stuff falling in from all angles, this stuff is going to smash into each other. And as it smashes into each other, it's going to heat up because it's smashing into each other so hard. As well as that, the odds that everything is falling in a perfectly balanced way are almost zero. There's always going to be like a tiny bit of like net spin to all this random stuff falling in. So what happens is all this stuff bumps into each other and smushes together and gets really hot, and you get this hot disk of gas orbiting around the black hole. This is what we call an accretion disk. And the only way that, well, the main way that you get gas from this disk onto the black hole is that it slowly cools down. It's so hot that it gives off a bunch of radiation. That means it's losing some energy, and it's slowly just sort of dribbling onto the black hole. Now, because this is really hot, it's actually really quite bright. And this actually means that you can see this really well, and that's what we call an active galactic nucleus if it has a particularly bright accretion disk. So, that's one of the surprising facts, is that even though black holes suck up things, in theory, they're actually often surrounded by gas, by this disk of hot gas. The other thing is that even though black holes themselves are dark, black hole regions are really, really bright because they have this really hot gas spinning around it, being really hot, radiating a whole lot of energy. And that's what we're seeing in this picture, is that we're seeing the accretion disk, this really hot disk of gas that's come from stuff falling in and smashing into each other and with a bit of spin forming a disk. And that radiation is bent by gravitational lensing to create this kind of effect with this sort of shadow of where the black hole is in the middle. But wait, there's more. So that's not the only gas that you've got around a black hole. So we've got this hot gas spinning around the black hole in the middle. We also have strong reason to believe that there's this cold gas in a much larger, what we call a torus, this kind of like donut-ish shape. We have a lot of, we have to say donut-ish or torus with quotes because if you take, there's a lot of research lately saying that it's not exactly kind of like a donut shape, and there's all sorts of, that's a thing. So the reason we think that's the case, that we have this sort of thick donut structure around it, I think we can, there's a slightly better, less MS Paint view of it. So what we do is when we look at lots of these supermassive black holes and galaxies, we see that sometimes we can see the accretion disk really nicely and all the sort of other stuff around the accretion disk really well. Sometimes we don't actually see it very well. It looks kind of obscured. It looks like there's a bunch of gas in the way. It's like there's some cloudiness between us, and literally we can call them clouds. This can be kind of clumpy. So the model that people have come up with is the idea that we have this kind of donut around it, and that sometimes we're looking right down the barrel and through the hole in the donut, and that means we can see this bright accretion disk. We see this, the full strength of the black hole accretion disk. But sometimes we're looking through all this gas, and we're seeing this kind of obscured black hole that doesn't quite look the same. It's got a lot of its radiation is absorbed. So to test these theories, to see like what actually is the structure of this torus and how does it actually work, and is our general idea right, we use observations. And by we, I mean not me, because I am a theorist, but I have friends who do this type of thing for me. And by friends, I mean my boss. So this is the VLT, the inventively named Very Large Telescope. This is the VLTI, actually, because it's got these connecty bits. It's the Very Large Telescope Interferometer. And what this is it's 4 telescopes linked together in Chile, and they use these 4 telescopes to get really high-resolution imagery of these black hole regions to try to see if we can see what the gas looks like. There's other things we use. So with that one, that's in the infrared, which is really hard to do, which is why there's only 4 telescopes, and I think they've often only used 2 linked at a time. This is the Atacama Large Millimeter Array, or ALMA, which is also in Chile. And this is an array of radio telescopes all linked up together to get a high-resolution view of this gas around supermassive black holes. So what should we see when we try to look at them? So the sort of schematic of what we're trying to look at is you've got this sort of hot gas accretion disk in the middle, and this broad, wide torus of like cooler gas around it that kind of blocks our view, at least partially, from some angles. But we don't have perfect resolution, so what we're really looking for is kind of something more like that. So you can't really see that it's a torus, but you can't really see the holes or anything, but you kind of see that it's wider in one direction than it is high. You should expect it to, you should expect there to be gas next to the black hole rather than above it. So what happens when we actually do these observations, and this is my boss's paper, you find the opposite, and this is the mystery. We would expect the gas to go this way, and we find it goes that way. We can do it with a whole bunch of other supermassive black holes and look at which way is the gas extended. And we see that, again, in all of these, in almost all of them, the gas, rather than going sideways, is actually above and below the disk of the black hole. And so that is our supermassive black hole space gas mystery. The gas around black holes is in the wrong place. It seems to be above the black holes and below the black holes rather than next to it. What's up with that? Okay, so here's our kind of picture of what might be going on. And the idea is that, okay, yeah, we do have this kind of disk, this torusy thing of cold, dusty gas, but that's not what we're actually seeing in these observations. What we're seeing is a wind getting blown out. Because this is warmer gas, it's a lot more visible, it gives off more light. What's happening here is that the radiation from the accretion disk right in the middle is slamming into the front edge of this donutty torus thing And the pressure from all that light, combined with all the heat that that light is imparting on the gas, is causing it to blow outwards. And it's this massive wind, this massive outflow of gas blowing upwards is what we're actually seeing. So that's a nice picture, but does it work? Do the physics actually add up? Is there enough pressure for this to actually come out right? And this is where I come in, because I work with computers. This is actually the Colosse supercomputer in Quebec City, which has now been decommissioned. I think it's quite a cool photo though, because it demonstrates what modern supercomputers actually kind of look like, which is that it's not just one big computer, it's lots of little computers wired up or connected in a massive network. That's part of why it's so difficult to do these big simulations, because you're not just throwing a problem at one computer and that computer's really fast. You have to figure out a way to get 1,000 computers to talk to each other in an efficient way, and so on. But anyway, we set up these simulations, we run them, and we see what kind of things do we see. We can actually replicate the picture that we came up with, that we get this kind of thing of the gas getting blown outwards. I think this is probably the best one to look at. We get this gas getting blown up and below the plane, and so we're getting this stuff that's extended up and down rather than sideways. And it's another view of what that looks like, is we have this big kind of, we call it biconical, it's like a cone above and a cone below, this big outflow flying up and a big outflow flying down, and this kind of obscuring structure in the middle. So that seems to be quite good. We seem to have shown that this model seems to work physically, and it seems to potentially explain the physics of what's going on. So is it mystery solved? Well, maybe. There's still a lot of stuff to go. We always have more work to do, and we've got to convince other people that it's true as well. But that's basically what we've found out, is that black holes have hot gas and cool gas around them. The radiation and what we believe tells us what we believe the reason why we see this gas above and below the black hole is because the radiation from the hot gas pushes the cool gas upwards, and that means we see the cool gas flying above it, and that maybe solves the mystery. Thank you.
Thank you very much, Dave. So do people have questions about black holes or supermassive black holes? Oh, there, yeah?
Why do we think that the hot gas in the accretion disk and the cool gas in the torus would be in the same plane, given that the black hole is close to spherical, so all directions are effectively the same to it? Why do we think they both form in the same plane? They form the same thing, or?
Yeah, so the idea is that you got this disk that's creating radiation. If you look at it from side on, you get a lot less radiation because you're seeing a very thin cross section. If you're looking at it from face down, you're getting a lot of radiation. So you would generally expect it to blow away gas that's above it and be more gentle to gas around it. So if you have gas above it, it doesn't really last for very long.
So if you disperse that, so it would survive.
It wouldn't survive. There are maybe ideas about, some people wondered if they are a little bit inclined and so on, but it seems like those will often start to self-regulate because this cold gas is very sensitive to the accretion disk radiation.
Any more questions?
What shapes the actual black hole?
What shapes the black hole?
Yeah.
I mean, it's round.
It's spherical, like a disc.
Yeah, so it's okay. So the thing is, to be honest, the black hole is so small compared to my simulations that it's just a dot, and I don't really care about it that much. But well, I care about it, I just don't know about it that much. So the basic thing is, yeah, if you have a super simple, basic model, Schwarzschild model black hole, it is a perfect sphere, and there is a point singularity in the middle, and that just comes from the physics of like, you can't, if anything deviates from that, the gravity is so strong it just pulls it into a sphere, basically.
It was a lot brighter at the bottom of it. Is that just the angle we're looking at it?
Yeah, okay, so this is the bit where you're getting into general relativity. I think what's going on there is that it's what they call relativistic beaming, which is that this is rotating so fast that it's getting close enough to the speed of light that if something is moving towards you, then the light is kind of getting bunched up in a traffic jam, because each time it takes a step forward, emits, takes a step forward, emits, it's kind of bunching up that way. So stuff coming towards you close to the speed of, at very high speeds, is brighter than stuff going away from you. I think that's what's going on. I'm getting a nod.
Yeah.
When you were talking about the size of the black hole you could get if our sun formed.
Yeah.
Black hole. So, with a supermassive black hole, what will have generated something of that size? I presume it's ancient. So
Okay. So the question is, how do supermassive black holes form?
Yeah.
The short answer is we don't know. So the basic thing is that there are some, we have some ideas of different mechanisms for how a supermassive black hole forms. So the idea is that in the center of a galaxy where these things exist, you do have the biggest concentration of gas and stars and stuff. So it sort of makes sense that you might form something massive there. You've got the most amount of stuff. But it's not clear what route that stuff goes to become a black hole. So some of the ideas are like that you just have such a big concentration of gas falling into the middle of the galaxy that it directly forms this sort of seed that grows into a supermassive black hole. Some of them have the idea that you start with like a very dense cluster of stars that turns into a bunch of neutron stars and black holes that then merge. And we do know that supermassive black holes merge with each other. So there's a bunch of ideas, and there could be it's either something merging or forming directly or something. But if you've got enough stuff in a small space, it's fairly likely.
Any more questions? Yeah.
So, out of all the movies that have black holes that you've seen, which one would you say is the most realistic representation?
The most realistic representation of a black hole. Oh, I don't want to say Interstellar. I think it was half right, but they kind of got some of the details wrong, and they did some weird, like they consulted the people, and they had a really nice picture, but it's clear that the writers didn't really understand what the picture was. And okay, so the thing about Interstellar, to get that level of time dilation, you would need to be like on the surface of the event horizon. You would be like pulverized by X-rays, and you probably would not have a stable orbit of a planet there. And the orbital mechanics make no sense. Okay. Screw it. I'm saying event horizon.
Any other question? No? If there's no other question, then let's Dave again. I think we are done for the evening, but of course you can stay here, enjoy a few more beers, I think. And yeah, thank you very much. And if you bought tickets for the events for tomorrow or Wednesday, then we'll see you again. So thank you very much, and then let's thank the speakers again.